I'm here to talk about machine learning for software engineers. I also want to talk about AI, but rather than keep saying AI or ML, I'm just going to say ML, just to simplify things. AI is just a sub-branch of machine learning, so it's kind of irrelevant which we get into. As Wes said, in a past life, I was the co-founder of SpringSource. So Java is really my background. I was once, generic Java developer, as Laura said. But I've made that journey away from Java towards using machine learning daily. I tried this first when I started Bamboo Loans. I had this crazy idea to leave Java and become a consumer finance person, which was a big mistake. I don't know anything about consumer finance. And I also failed quite miserably to embrace and roll out machine learning while I was there. Yet for some reason, I ended up joining a machine learning startup where we use AI and ML to try and solve the problem of performance optimization. And what I want to do is talk about what I did wrong at Bamboo, what I've done right at Skipjack, just kind of give you all a sense of how a software engineer, we should all care about machine learning and how we can actually do something meaningful with it. But let's start with the story. My best friend is moving house, and he knows I'm a bit of a smart home geek. So he asked me, hey mate, I want to be able to speak to a thing to make it do things. This is his whole specification. And he's an Apple nerd, so he's really optimistic about the Apple HomePod. So I went to try it out, and the speaker is incredible. If you've not heard it yet, you should definitely try it out. But at my house, I've got a ton of these Sonos One speakers which have Alexa built in. And I've not really used Siri all that much, but I'm a big Alexa fan. I'm trying to make sure everything in my house can be controlled by Alexa. Most of the time it doesn't work, so it ends up taking a lot longer than it would to use the normal controller. My wife's in the front row and is no doubt nodding her head. But Alexa, it does work, and when it doesn't work, it has really good diagnostics as to why it doesn't work. I was quite saddened when I tried Siri. It's not the same. I use an app called Todoist, but to make Siri understand that, you have to call it Tardoist. And this is such a known thing, it's actually in the FAQ on the Todoist website. And my kind of point here is, good quality machine learning is a competitive advantage. My friend, who is an Apple nerd, is going to go and spend a whole bunch of money with Sonos and get into the Amazon Alexa space because his use case is voice recognition. He wants to be able to use his voice to control his new house. And obviously Amazon, as we know, have invested a ton of time, and a ton of money, and a ton of engineering resource, a ton of expertise in getting that problem solved just right. They've done a really good job. But I think we need to think further than that. Yes, it's great to say that machine learning is a competitive advantage, but it's also becoming competitive necessity. I'm sure you've all heard the term democratization of AI, democratization of ML. I think it's a complete misuse of the word democratization, but in essence, it's saying everybody in this room and everybody in the world at large has access to all the building blocks, all the algorithms, all the tools, all the compute needed to do good quality machine learning. The investment you need to make now to do an ML solution is tiny. And this can be something as simple as, hey, I can download TensorFlow online, I don't pay for that, I get a really high quality neural network toolkit. Or it can be, hey, I can go to Google Cloud, or I can go to AWS, and I can buy a bunch of compute for a couple of hours, a couple of days, train some models, great. Or, if you really want to go far into it, you can pay Amazon $4, send them 1,000 sound files, and they will run them through the Alexa engine. So there's no barrier to being able to get access to the raw materials needed to do good quality machine learning. And because of this, I think it's fair to say that machine learning is what's next for software engineers. We've spent a ton of time getting into microservices and containers and DevOps and all these cool things that discuss how to build software better, how to deliver that software better, but none of those technologies really focus on the what that we're building, the solutions that we're delivering. Yes, they talk about how, the shape, if you will, but not what it is. Machine learning is different. It focuses on changing our mindset and giving us new tools to build solutions we couldn't even imagine. My favorite one at the moment is neural style transfer. If you've not seen this, you have an image, maybe it's a photograph of you, and maybe you've got a photograph of a mountain, and you can transfer the style from the mountain image onto your photograph and make it look like you've got this nice sunset on your head. Incredible, which I can't even conceive how I would write an algorithm like that without machine learning. And this is probably the point I want to highlight the most, and it's something that's going to permeate the entire presentation. And I will say, this is the most pretentious slide in the deck. It's like I'm trying to be some kind of thought leader, but I'm not. There's an important idea here. When we write software today, we write the algorithm, we write the series of steps that you need to follow to solve a problem. Maybe that is the series of steps to crop an image and put some text on it and make a meme. You know, we write those steps. With machine learning and with AI, it's not like that. We write the algorithm to find the algorithm. We describe how to find out how to solve the problem. So we're one step removed from the actual details. We're one step removed from the actual set of steps, from the actual algorithm that does what we're trying to do. And that level of indirection, that how of the how, ends up permeating everything you do in a project. And I want to touch on that quite a bit as we go through this. One of the frustrating things being in the ML space is the number of people who just seem to discount it out of hand as the latest hype. And I hear the word magic used a lot. This assumption that there's like some magic and it doesn't really work and we're best off just sticking to traditional software engineering practices. And what I often hear people say is, oh yeah, I'll just get a ton of data and throw it at a neural network and a problem gets solved. And that perception, I think, is dangerous because it's not really how machine learning works. And it certainly is it misleads people into believing that there's some kind of special source that only works in certain cases. The reality is quite far from that. I like to say this, good models don't happen by accident. The reality is, having done this for a fair few years now, building a machine learning solution, building a good machine learning model is just as much software engineering practice, if not more actually, than traditional software engineering. You still have to iterate towards a solution. You still have to have good testing practices, good version control practices. You still have to have good data practices. Everything you do as a software engineer today, you need to do just as much, if not more, to make machine learning work. It isn't a case of take data, take a neural network, smash them together, and get a solution. It really does require good quality engineering. So if we want to build a good solution, if we want to engineer a good solution, how do we do that? And I think one of the first things we all need to do is avoid making the mistakes of the past. We all, I'm sure, know what DevOps is. If you don't know what DevOps is, there's probably going to be plenty of talks about that at the conference. But in essence, it's this idea that keeping the people who build software separated from the people who deploy that software and support that software is a bad idea. Those are not two separate things. They're one part of the same whole. They're one part of delivering value to end users. It's silly to assume that there's a world in which one set of people can build the software, throw it over the wall, another set of people support it. It doesn't work that way. So we've learned that munging that together, creating this kind of co-practice of DevOps, of build, test, deploy, feedback, and iterate is the best way to build software. And in tomorrow's keynote, Laura's going to talk a little bit more about how security fits into this world. You know, in the recent times, we've all seen the increase in crazy security exploits that seem to be occurring ever faster. And one of the logical steps you might take is to think, well, maybe it makes sense if the people who are building the software and supporting the software have more security expertise, have more security support at the time they're doing it. We are very much in danger of making the same mistake we've made in the past and assuming that, well, I'm going to have a team over here who's building the software. They're doing the DevOps stuff for this piece of software. But the actual algorithm that we use to deliver value is sat way over here in a data science team. And those two are not going to meet at all. That's not going to happen at all. And of course, this has all the problems from the past. In fact, when I first joined Skipjack, this was the first thing I encountered. it was day one, and I remember very vividly that the team who were working on the machine learning model was not the team who were actually wrapping that model up in software and delivering it to our users. But moreover, the team who were building the model had no domain experts in there. And we were building performance optimization software, and the team building the model didn't understand performance optimization. So obviously that was already a recipe for disaster. Really simple move, just co-locate those people together, get them pulling in the same direction, and all of a sudden a whole bunch of problems we had just disappeared. There was no longer this incredibly long and arduous feedback cycle from, here's a model, let's try it in production with real data, get some results and feed it back. But also we were able to figure out, and I'll touch on this a little bit later, there was quite a lot of bias in our model. We were using the wrong metrics. And that only became apparent when we got everybody working in the same room on the same problem at the same time. And I think Babe Ruth said it best. Babe Ruth said it best. The way a team plays as a whole determines its success. A bunch of individuals all pulling in different directions is never going to be as strong as a team with a singular focus. They all have to play together to be successful. When you start thinking of this, though, the first issue you'll come across is this tension between generalization and specialization. And I've seen this more starkly when trying to build machine learning teams. I'm sure we've all heard that to do machine learning, you have to have a PhD. We're going to learn that's not really true. But it does help to have people who've got deep theoretical expertise around when you're trying to build deep machine learning models. So you definitely want specialists. And if you're doing some domain problem, you want domain specialists. We wanted somebody who was a performance specialist. And you probably want somebody who's a user experience specialist and probably somebody who really understands deployment and testing. So you do want specialists, but somehow you want generalization as well. You want all that to mesh together in a way that creates a really solid solution. And I've seen various different approaches to this. One is to just assume that everybody can learn everything. And that may be possible for simpler software solutions. If you're building a very simple website, basically a CRUD application, it may be possible for everyone to learn JavaScript and everyone to learn Java and everyone to learn Docker. But it's not possible for everyone to understand all those things and all of the machine learning stuff at the same time. So instead, I like to think about it this way. A successful team, a successful project, has individuals who specialize, and then the teams of those individuals work to generalize. They work to bring all those different strands of expertise together and create a general solution, a solution that's fit for human consumption. Because at the end of the day, that's what we're trying to do. We're not building a machine learning model for the sake of it. We're trying to deliver actual human value, voice recognition, self-driving cars, neural style transfer, something that people care about using all of the different skills we have in our teams. Now, of course, if someone's going to specialize, or if you're going to work within your team to integrate some of those specializations into a Java solution, a C# solution, a Python solution, then there's lots of skills to be gained. You have to upskill. Now, nobody would be in this room if they were afraid of learning new things. Everyone's here to learn something, I'm sure, or maybe just to have a few days off work, I don't know, or maybe both. But we're all here to learn. And the nice thing about machine learning is there's loads to learn. But the other nice thing is you can be really effective really early. You don't have to learn everything. You don't have to get a PhD to be effective. It's one of the most rewarding aspects, actually, of trying to get into machine learning is how fast you can be productive. That's not to say, though, that you can't get it wrong. Because when I first tried to learn machine learning and become somebody who could build machine learning solutions, I made an absolute hash of it. I got so disheartened, I gave up. And it wasn't for another 3 months until I built up the courage again to revisit the problem and think, maybe there's a better way. I can't be the only person who can't learn this stuff. I need to figure it out. So I'm putting this up here as a kind of summary of the things that you might need to learn, but also to say, you don't need to learn all this at once. This is maybe where you're heading. This is the journey. This is the destination. But the journey is completely different. You can learn little bits of this as you move through, as you build up a familiarity, and eventually out the end comes somebody who's an expert. What I also want to dive into, though, is what's the most important thing to learn. Some people will say, go learn the theory. In fact, I was just browsing Twitter yesterday, trying to see what the latest sentiment is about machine learning, and there's lots of use of the word magic. But also, there seems to be a real sentiment that if you don't have deep theoretical knowledge, then you can't possibly get involved with machine learning, which is crazy to me. That's kind of like saying, if you don't understand the precise details of how a CPU is made, you can't be a Java developer. How dare you? It's nonsense. Yes, the theory is helpful. Yes, the theory is important. But you don't need to understand it at a very deep level to be productive. What about practice? What about practical skills? Well, of course, they're super important. Because without the practical skills, you're never going to build anything. If you can't code in Python and you can't use NumPy and you can't use TensorFlow, you're never going to be productive. But what order should you learn them in? What things matter? Let's dive into that. And then this last column, intuition. Typically, people would leave this out. But what I found, and where my mistake was, learning the intuition and actually learning it, going out specifically with this idea in mind that you would learn all the intuition behind machine learning is what helps the most. It's what helps you stitch together these kind of disparate ideas about your domain knowledge, your software knowledge, your users' problems, and how you might solve that with a machine learning model. It's the intuition that matters the most. I desperately wanted this to be a path. I wanted to be able to have a slide that said the learning path. Learn this theory, learn this intuition, learn this practice, or something like that. But it doesn't really work that way. Instead, you're constantly iterating towards deeper and deeper knowledge. I like to imagine it, I got stuck on a plane, obviously because of the snow last week. I was hovering around Heathrow, 37,000 feet, 38,000 feet, 20,000 feet. You know, you're kind of circling around being an expert at the runway, and eventually you get there. But as you circle, you're getting value. You're learning more and more about the problem space. And as I say, you can be productive very, very early. I want to dive into this idea of intuition a little bit more. I can't understate the importance of it. My big mistake when I started out was I went straight for the theory. I got all the textbooks that everyone gets and just started reading them, started working through the exercises. But I never really understood from those textbooks the why, the essence of it. So when I started again, I set out specifically to try just to figure out, like, what is a neural network trying to do? Is this whole idea that it's really modeling the human brain an accurate model I can think about, or is there a better model? What am I trying to do when I'm doing classification? What am I trying to do when I'm doing regression? Just trying to understand, like, really what those things mean. And there's a great Einstein quote where he says, intuition does not come to an unprepared mind. And to me, this means you have to be open to intuition. You have to go out and seek it. It's not just like a flash of inspiration. It's something you actively learn. And I encourage everybody here, if you're going to try and learn machine learning and try to learn artificial intelligence, that you start to build those intuitions. But of course, at some point comes learning the practice. And everybody in this room already has a head start when learning the practice of machine learning over somebody who has never been a programmer before. Because much of what you do when you're building a machine learning model is write code, test that code, rewrite it, retest it, rewrite it, retest it, again, and again, and again, and again. In fact, you will probably iterate more on the same 200 lines of code when building a model than you ever would do when building a normal piece of software with Java or whatever. It's a very small amount of code that you spend an immense amount of time on. And I want to give you a little bit of insight into how you might take this learning journey, what worked for me, and what you're going to see. The first question, the most important question, is do you learn R or do you learn Python? And now, if anyone's seen any of my presentations on data science in the past, I'm a huge R snob. I learned R first, and because of that, I've got this unnatural attachment to it. But the reality is, if you're reading papers in the space, if you're trying to hire people in the space, if you're looking at most of the learning resources in the space, Python is the language of choice. It's rare to find online tutorials and lectures in R. Most of them are in Python. That said, there's no harm in learning both. You can definitely find kind of different tutorials in the R space than you can in the Python space. But if you're starting, Python makes sense. If you're setting up a team, in particular, Python makes sense. Now, I'm obviously hiring people in this space. Very, very rarely do you come across somebody who's got R experience. It's much more common to see someone with Python experience. And obviously, as Java developers, as PHP developers, as C# developers, Python is much more familiar to our mental model than R is. R is a different beast altogether. So Python is the way. The next problem you're going to face when you come to do some kind of deep neural networks or something in the AI space is, which framework do you use? Now, I've only got 4 logos on here, but if you're a JavaScript developer, you're going to be very familiar in this space because there are hundreds of these things, and there's like a new one every day. Now, of course, TensorFlow is the popular one. It's the React of the deep learning space. And the natural inclination, I think, for everyone would be to go to TensorFlow. Well, that's what Google did, so it's got to be TensorFlow. At some point, you will learn TensorFlow. At some point, you will build a solution either with TensorFlow or with some framework that is backed by TensorFlow. But when you're starting, the absolute best framework to start with is PyTorch for a very, very simple reason. When you're debugging it, when you're running through the code and stepping through it, it works exactly like code you write today. You can step through it with a debugger. You can use printline. You can apply all of your normal debugging practices. That is not true of Keras. That is not true of TensorFlow. That is not true of MXNet at all. PyTorch is a completely different beast, and it works in a much more familiar mental model that we would all be used to as developers. Now, I put theory last, not because I think it's the least important, even though I actually do think it's the least important, but because I think it's the thing you should attack last. You will find learning the theory after doing some practice, after learning some intuition, much easier, because some of the textbooks and some of the tutorials are just impenetrable. Anybody do computer science or maths or statistics or anything like that at school, and you read the textbook, and then there's that fateful sentence, and it follows that. And you've gone from simple example to example that then takes you like 15 hours to unpack in one sentence. And that's very much the machine learning literature completely. So you need to, I think, have all that intuitive knowledge, have all that practical knowledge before you start. But what I did find valuable about the theory is it helped me think about the world in a completely different way. I was once told that learning Lisp would make me a better programmer, even if I never used Lisp. This seems to be the pervading Lisp myth. I've never really managed to actually get any practical experience with Lisp, but I did learn Haskell. When I learned Haskell, this happened to me. I had this sort of like moment of seeing the Matrix, and immediately I could write better Java code for some reason that was inexplicable, but it was just a different mental model. It was different connections in my brain. And the only other time that's happened to me in my entire life is when I really got deep into the machine learning literature and tried to learn some of the theory. But it wasn't the neural network theory, it wasn't all the deep learning theory. What actually had the biggest impact on me was really getting a solid understanding of statistics. Because as developers, we work in a very deterministic world. Everything's very clear-cut and laid out, or at least we like to pretend that it is. Learning statistics and learning probability and really starting to think in those terms really changed the way I think about the world. Now, the absolute hardest part of learning machine learning and AI is finding the right resources. This reminds me a little bit of what it was like trying to learn Java in the old days. Does anyone remember those Sam's Learn Java in 24 Hours books? Yeah. How is that ever going to be the case? It's nothing like that exists anymore. It's like there's no learn yourself deep neural networks in 24 hours, but there are still a great many bad quality learning resources out there. And lucky for you, I've spent money on all these things and wasted innumerable amounts of hours on all these things and managed to whittle it down to ones that work. If you only buy one book, if you only read one book on data science and machine learning, it should be this one by Cathy O'Neill and Rachel Schutt, Doing Data Science. There's no other book I've read that has that perfect mix of theory, practice, and intuition. It's very clear that this is from people who are in the trenches building real solutions. Yes, they understand the theory, they also understand the practice, but they also understand like intuitively what they're doing. I'd waited a long time for a really good TensorFlow book, a really good kind of like deep learning, hands-on, practical book. I recently got this one, hands-on machine learning with scikit-learn and TensorFlow. Can't recommend it enough. It's one of those books that just flows. You know when you're reading it and step to step to step, you don't want to put it down. It's a really, really good book. Sadly, I haven't managed to find a good book on PyTorch yet. What I have found is that all the examples in this book port really easily into PyTorch. And when you're trying to expand upon them, when you're trying to build your own models, that's a really good step forward. Traditionally, I've always been a bit of a book learner. I really just didn't like watching lectures online. It just seemed a bit too much of a time waste. But I bit the bullet and got into data science through this course on Coursera, Data Science Specialization. It's all done in R, which is what kind of sparked my love for it. Brian and Roger work at Johns Hopkins, so it's got like a real biology, biotech sense to it. Great data sets, great practical experience, definitely worthwhile doing. Without fail, without a doubt, though, my favorite is the deep learning specialization from Andrew Ng. So this is, I don't even know how to describe it other than to say, once you start, you will not stop. It's really hard to say, yeah, I'll just stick to doing one course at a time in 1 week, rather than jumping ahead 4 weeks, 5 weeks, 6 weeks. He's a great teacher, there's some great data sets, there's great practical experience, and really quickly you're building things you just thought, how is that even possible? I think like week 4 you build a neural style transfer system, and it's amazing. If you're trying to dive into the theory, these have got some theory, but if you're trying to dive deeper, then you absolutely cannot go wrong with Gilbert Strang's MIT linear algebra course. If you haven't already watched this, wow. Gilbert Strang is this amazing lecturer. If you don't like linear algebra, you will do after this. Somehow he manages to make it interesting and exciting. And then Jim Fowler, calculus. There's a bit more calculus in deep learning than there is in most programming. Definitely worth doing. Jim is this kind of hyper-active, super enthusiastic human being. I've never met anyone quite that enthusiastic. So sometimes I'll just watch the video, something a bit down. Yeah. A little bit of chain rule now and again, it's great. Those four courses, those 4 series of lectures will absolutely be enough to get you started. But where machine learning really excels as a learning journey, where it's one of those, you just don't get this with normal software engineering, is in the availability of problems and data sets. There's just a massive library of great data sets and problems to solve in the world, and they're all collected, by and large, on Kaggle. Has anyone used Kaggle? Like 2%. Wow, try Kaggle. So essentially, people are just putting challenges online. Hey, here's a data set, here's a problem I'd like to solve, try it out. And you can try them out for fun, or you can try them out and try to win $10,000, which is always good. But essentially, you're getting real problems and real data to try and learn machine learning. This is much better than continually using the same data set over and over again, continually trying to create fake data sets. And if you're early in your journey and you don't have enough data to actually do something meaningful, this is the place to go. I'd say that if you follow those courses, if you read those books, if you do some Kaggle, you can actually be pretty productive. I was building models for work not long after doing that, ones that actually worked. I really strongly, 100% disagree with the comments of people saying, you have to know the theory. It's too dangerous to build a model if you don't know the theory. Because that assumes that building a model isn't just software engineering practices. You're still building a model, and you're still testing it, and you're still, is it fit for purpose? You're still iterating on it. All the things you do when you're building your algorithms yourself, you still do. So those kind of mechanistic bits are easier, I think, than what happens when you get deep into it, when you start dealing with the nuances of a model. And I want to talk about 2 particular things, because when you really start putting models out in the wild, and when you really start seeing them be used, the 2 problems you're going to face are not technical ones, really. They're more like sociological problems, and it's bias and explainability, transparency. Bias is everywhere. And the first place you'll see it, and almost certainly the first place you'll encounter it, is human bias, the bias that you introduced, the bias that your teams introduced. So you'll remember early on I said, when I started at Skipjack, we had a data science team and we had a software engineering team, and that was leading to bad solutions. But one of the things it led to was a complete bias in the results. Now, has anyone ever heard of Goodhart's law, We've probably all seen it. When a measure becomes a target, it ceases to be a good measure. It's for this reason that we don't target software developers on the number of lines of code written. Otherwise, every valid white space break would be a new line. Machine learning is really susceptible to abuse of measurements when they become targets. If you're trying to regress some problem or classify some problem, or you're trying to use, in our case, an optimization problem, you're measuring something, you have some kind of target in mind. And in our case, it was performance improvement. We wanted things to go faster. And in that little phrase, performance improvement, is the danger. What do you mean by performance improvement? We had contracts with customers where we were promising performance uplift, and they were promising money. So of course it becomes really key that you get the best performance uplift. And the CEO at the time was saying performance uplift, and he was saying this to the software engineers, and they were going, okay, cool, performance uplift. And they were saying that to the data scientists, and they were going, okay, cool, performance uplift. Don't really know what that means, but it is a target for us. So they found an algorithm that basically calculated the maximum improvement between any two measured points of the system before and the system after. It could be, how fast was the system when there was one user on it beforehand, and how fast was it when there was 100 users afterwards? It could be anything. No real-world applicability for this measurement whatsoever. It was just the biggest measurable distance in our data set. And of course, this introduced a huge amount of bias, and when you rolled this out into the real world, you didn't see those improvements because they weren't measuring the real world. So as humans, as engineers, you've really got to know what you're doing. You've really got to be clear and focus that the measure you're optimizing to, the measure you're regressing for, the measure you're classifying around is what you're trying to achieve, lest you introduce this kind of bias. But thankfully, you can typically spot that bias quite easy. All it takes is someone who knows what they're doing to go, hang on, that doesn't make any sense. A bit more pervasive, a bit more insidious is data bias. Now, anybody here care a little bit about GDPR? I thought so. If you're not in the EU or trading with the EU, GDPR is the General Data Protection Regulation, whole new set of laws, mostly very welcome, that govern how organizations deal with public data, with individuals' data. And I'm not going to read all this out, but the essence of Article 9, Section 1 is it's now no longer legal, or won't be as of May, June, legal for organizations like mine to make decisions based on data that discriminate against individuals because of their religious background or philosophical beliefs or sexuality. This is now prescribed in law. So obviously, this is somewhat easier if you're writing the algorithms yourself. If you're writing an algorithm to make a credit decision on somebody and you're writing the steps yourself, you can check that you're not using any religious preference data or genetic data or biometric data. You can check that. It's definitely work, and it's definitely something we all have to put some effort into, but it's something we can do. With machine learning, it's a little bit harder. Step one is to avoid all data bias by stripping that data out of your algorithms. And you may be feeding in some of this information into a neural network, and it may be figuring out, okay, well, for some reason, I don't know, trade union membership has some relevance on the outcome. That's the data bias. But even that's quite easy to solve. Even removing that's quite easy. The real danger is learned bias. What happens if we remove all that data, remove all that potentially discriminatory data, but somehow the bias creeps back in because the machine learning model learns to be biased? Anybody heard of Microsoft Tay? Yeah, that was a shame, wasn't it? I mean, we're laughing, but it's not really funny because it is something that machine learning models are really susceptible to. You can, based on input of data or based on kind of the tendency of the networks and based on what's going on in some of those deep neural networks, these models can be learned to be biased. I mean, in this case, it learned to be horrendously racist and genocidal. But it can be a lot less apparent than that, but not any less important. Let me give you an example. When I tried to get into the credit space, I thought, I know nothing about credit, I'll go and talk to people who know about credit. So I spoke to an old school credit underwriter, just pearls of knowledge. And he was telling me that one of the things you can do to detect somebody's ethnicity is look at strings of consonants and vowels in their second name. So maybe you've removed the data about ethnicity from your data set, but you're still putting surname in your data set. And maybe, and if you've ever seen like edge detection and face detection work in a neural network, you'll see that these patterns can be spotted. Maybe the neural network learns, hey, there's 15 consonants here in this one name, that must be, I don't know, from Manchester. Learned bias is really pervasive. I don't know, I pressed the button. There's not a great deal of research in this space. There is some, but it's not. I don't think this is really going to be something we're going to solve with research or with new algorithms or fundamental changes in the next few years. This is where engineering comes in. If you go to the security track, probably you're going to hear quite a lot about like adversarial practices in security, things like penetration testing and so forth. The same is going to be happening here. We're going to end up having adversarial techniques to try and detect bias in algorithms. Can you find some way, like the people on Twitter who completely screwed up Tay, can you find up some way to feed data in to a neural network, to a machine learning model, to make it exhibit this bias? The only way, I think, to spot bias is to actively make engineering for it and testing for it a part of your process. It's not going to be as easy as, hey, the Python code says there's bias in this model. You're going to have to engineer towards a solution that doesn't have bias in it. Now, bias is really important, and I put it first because I think of all the kind of sociological issues around machine learning, it's probably the most important one. And Tim Kadlec is doing a talk on data bias and similar bias aspects on Wednesday. So if you're more interested in that, you should go and see that. And obviously, there's the AMA afterwards. But a more personal one and frustrating one for all of us is transparency, or as I like to call it, computer says no. So I went to the Apple store about 12 months ago to buy a new iPhone. And the person there convinced me, hey, you should get on the iPhone upgrade program. I thought, this is a great deal. New iPhone every 11 months, great. So I went through the whole process, couldn't get the credit. No, you can't have a new iPhone. Okay, any idea why? No. No explanation whatsoever as to why I was not eligible for the iPhone upgrade program. The computer just simply said no. So now I had to pay for a new iPhone every 11 months, like a Neanderthal. But it's funny, but it's frustrating, because we've all been victims of this. We've all had a scenario where you've tried to do something with a computer and just inexplicably no, you can't do it. Tried to cancel my TV license yesterday. No, don't know why. Couldn't do it. This is even more likely in the world of machine learning, simply because you don't know the steps the algorithm is taking to explain the decision. If you've written the steps that says why someone from Manchester can't have an iPhone upgrade, then you'll know it's because you're from Manchester. But if the machine learning model has learned this, you don't know why that is. You've got no idea. So thankfully, the future is a little bit rosier here. There's always some great research in this space around explainable networks, explainable algorithms. There's a big project at DARPA. But actually, we also have, again, traditional engineering practices, traditional organizational practices that we can use to work around this. Anyone who's ever worked in a regulatory business or anything that's kind of got like a regulatory constraint will know the idea of compensating controls. This is where your system can't do something, so you have to put like a human element in the way or some other backup system in the way. And all I would have needed from Apple was for them to say, well, we don't know why, let's have a human look at it. And this is, I think, just enough to say that whatever solution you're building, it isn't magic. It might solve the 80% case, the 90% case, the 95% case, but at some point, it's going to do something that you're not quite clear about, and someone's going to have to get involved. If anyone's ever bought anything from Google, like Google Enterprise or anything like that, and you've realized it's just impossible to get support from them, don't let your organization get into that space. Be ready to explain, or at least override, why your models are doing what they're doing. So I just want to summarize really quickly, because I'm getting the stop sign. If you were already ignoring software, if you were ignoring machine learning, if you were ignoring AI and thinking, hey, this is just some kind of overhyped magic, don't do that. I mean, look around, you can already see there are some great solutions in this space. There are more solutions coming all the time. And at some point, it's going to become a competitive necessity for you and your organization to really understand how to deploy ML in your space. But don't be disheartened, because most of what you do in machine learning is mostly software engineering. Now, it's only about 5% of the time do we really do any fancy maths or anything at work. It's mostly just, oh, let's just try this in a model and test it and roll it out and iterate on it. Exactly the same as we've done with everything else we've ever built. Probably the most important thing I want to say, or the two most important things I want to say, are don't make the mistake of old. Don't try and have a data science team and a software team. Co-locate those things together. Make sure that everybody has an understanding of what everybody else is doing. And I know it's trending to say it, but I see it in my day job, so I'm not saying it for trendy reasons. Now more than ever, ethics does matter. You're going to be one step removed from any kind of ethical violation or ethical issues. So you have to actively integrate testing for, checking for ethical violations in your software. And my final point, because it's why I'm here doing this talk, there's a lot to learn, but it's a great amount of fun. It's all very, very valuable. And even if right now you're not using ML or AI at work, you will find these techniques, these technologies, these theories so valuable and so mentally stimulating. I just recommend diving into it. Thank you very much.